lecture is IP telephony or voice over IP. I would like you to refer to your textbook by Roger L. Freeman uh, and see the chapter number 12 in that. Uh, we are referring our discussion from that particular chapter, but uh, we'll be discussing it in a summarized manner. I have already uh, shared um, this particular presentation as well as the presentation that that is based upon chapter number 12 of this book. So let's start. First of all, uh, we need to know that up till now we have been uh, looking after the telephony network, which was basically required to provide connectivity from one end to the other on on for a human voice communication. And as you know, we have already converted the voice from its analog format to the digital format. Now, what we are planning to do here is that we need to convert it further into the IP format so that we can take our voice from one place in the world to another place over the IP network. As you know, the IP network is available all over the world. Even if we do not have a telephone exchange at a certain point, the availability of IP network is more probable. There is more probability that an IP network is available at a particular point in the world. That's why we are. It has been tried and successfully um, handled voice over IP. So let's see what are the problems that were faced and how does such a network work. While we do have our knowledge of our DS zeros and E zeros, which are 64 kbps um, voice converted into digital signals, and their uh, multiplex signals, which are, for example, E1s or DS1s, and further uh, multiplex multiples. So, how do we do that in IP telephony or voice over IP? And similarly, as we have seen the signaling systems and signaling system number 7 in particular in our earlier discussions, we'll see how this um, signaling is done in voice over IP. As you know, that establishment of a call, monitoring it, and then after all tearing it down is also required in a voice over IP network. So what we need to do is to send our voice over the internet protocol, and as but uh, with internet, you're already familiar that it provides us um, the service of World Wide Web, which is sent over a fifth layer protocol, which is called HTTP, or the mail, which is sent on SMTP, or the DNS server, which is uh, yeah, which is also on the fifth layer. Similarly, if you send a file over over an IP network, we would use an FTP protocol, which is also a fifth layer protocol. Um, but in most of these cases, it is not required to ensure uh, that that our sent information gets to the other point exactly uh, uh, in sequence and with a short delay. We can have multiple delays. We can have um, packets coming to the other end in off sequence way, but using the sequencing protocols, using our protocols, we can do that sequencing also. So what would happen if we have voice? Because while we are talking, one word comes before the other, and another comes before that, so the sequence has to be maintained. If some of the packets are dropped or or end up in a faulty way, what would happen? We'll see what is the solution that voice over IP protocols promise. How does it work? First of all, it continuously samples the data, samples the audio signal, which is basically an analog signal, then converts each sample into the digital form. That this is the same thing that we have already studied in our PCM part. Then this digitized stream is sent across the internet in the form of packets. As you know, the digital packets, in the digital packets there are two parts, the overhead and the payload. So the payload part is filled up with those digital streams, digitized stream of uh, uh, stream that we get from the A to O converter, on which the input is the audio analog signal. Now, after that, after getting the packets, uh, they are sent over the IP network, and on the other end, they are converted back uh, to an analog stream for playback. Now, why do we want to use voice over IP? Because it is economical. The traditional switching systems and equipment are much more costly as compared to IP telephony. So, what were the challenges that were expected while sending voice over IP protocol? First of all, we would expect some voice transmission delay. As you know, uh, there is a considerable delay in case of IP communication, IP networks, because the IP networks, IP packets undergo a lot many types of delays. There may be the propagation delays, uh, the transmission delays. Then we have got a very important delay, which is basically the processing delay or the queuing, and then the queuing delay. So that are inherent to an IP network. Then what would happen if we have a voice signal to be transported over the other end? So, and how can we do that? How do we do that? We first of all, if we want to have to confirm that our packets do not have to wait at different interfaces along the path from one point to the other, then we should have its preference. We can set the preference, and there are many protocols used in the TCP/IP suite, and further more in the MPLS domain also, in which we can reserve their reserve certain reserve top priority for certain types of packets. Uh, and such packets would be definitely real-time packets. They can be of voice over IP or video over IP, because if some of the packets get lower delay and others get more delay, what would happen is that the sequence would not remain the same, and it would be difficult to replay the exact voice or the video on the other end. The second problem or the challenge that is expected in voice over IP is the call setup. Just like in signaling system number 7, we have a process of call setup. We need to have a process of call setup in voice over IP also. And thirdly, we need to have a backward compatibility with the existing PSTN switched telephone network. Now, two organizations, before that, going to that, I would refer you to page number 485 of your book of telecommunication system engineering, from chapter number 12. This gives some other challenges also that were faced while developing voice over IP, and those were first of all the delay, which included the mouth to ear delay, then the impact of error frames, because we might have received some frames which come in error, then we might lose some packets or the frames. How do we handle that? That needs to be seen. Then there is a variation of packet arrival time or the jitter. Then the prioritization of voice over IP that I just talked about earlier. Then the talkers, echo, distortion, sufficient bit rate capacity or interconnecting transmission media. Then optimized standard packet or payload size, because as you know, in IP networks the packet size does not remain the same, but if we use IP packets for a real-time protocol like sending voice over it, we need to have similar size packets or an optimized standard packet size for communication. Then there is definitely a packet overhead, which definitely is a toll on our communication, which takes up the transmission resources, right? So instead of sending only the payload, we are also sending some overhead, which is a part and parcel of our IP net packet. Then we need to have silence suppression, because if we do not, if somebody is talking with intervals in between, so that the silence in between might instigate the other side to understand that the other side have the first side has hanged up. So to ensure that both of these are online and they should know that the other one is online, a silence suppression noise is particularly injected for convenience or comfort. It's also called comfort noise. Now let's see what are the IP telephony standards that are used in the world. Both of major organizations, from the telecommunication side, it is ITU, and from the internet side or the IT side, it is IETF, which is Internet Engineering Task Force. Both have both have developed their own standards for IP telephony. So, what is the basic process of sending voice over IP? Both of these groups, ITU and ITF, agree on the basics of encoding and transmission of audio. Thanks to our basic standard of PCM, audio is encoded using a well-known standard, which is PCM, which includes both the American and European standards, that is DS1 as well as E1 standards. So the audio is transferred using the real-time protocol. Real-time protocol is basically placed at layer 5. Uh, Real-time message is encapsulated in a UDP datagram, which is further encapsulated in an IP datagram or the third layer datagram for transmission. Now, why UDP is used? UDP is used because of its lower overhead, and there is no retransmissions. And if we have audio to be sent, it, it is not feasible to have its packets retransmitted. And the audio must be played as it arrives. Secondly, the playback cannot be stopped to wait for the retransmitted packet. We cannot wait uh, for the actual packet that should have been reached the destination earlier. Uh, Basically, since it is a full duplex communication, two independent RTP sessions exist. Uh, because we have to send some outgoing data and we have to receive some incoming data. In that way, we have a full duplex communication, which means that we are talking while we are listening also. Now, what are the signaling systems that are used in a voice over IP system? And this is the main complexity of the voice over IP systems. And how do we manage the calls? And this is the same problem that we faced while we had our PSTN voice, which was initially uh, an analog voice which was converted into digital format, into DS0 or E0 format. Then it was multiplexed into E1s. But all this system needed signaling, and the same signal, and in that case, signaling system number 7 was used. But in voice over IP, we have got uh, a number of options. But all these options have one thing in common, and that is their backward compatibility to signaling system number 7. So the signaling protocols in voice over IP are session initiation protocol, which is developed by IETF, and it is called SIP normally, and S.323, which is developed by International Telecommunication Union. There are other um, protocols also, which were jointly made by IETF and ITU, so that such protocols are could be used in all the uh, equipment, because some equipment might be working on SIP and some would be working on H.323, but um, the purpose of developing Megaco and MGCP were to develop such protocol, such signaling system, which which is acceptable to both the SIP and H.323 machines. But as I already told you, voice over IP signaling protocols should be able to interact with SS7, which is already in vogue all over the world in the PSTN Now, this diagram shows you how two IP telephones can talk to each other, can start and initiate a communication, continue it, and then tear it down. How is it possible? Within the internet, there must be a component connected to the internet, which is called the media gateway controller. And at both the ends of the internet, we have got an IP telephone. You might have seen some IP telephones physically also. I would refer you to see an IP telephone made by Cisco. You can see that on the internet also. Just Google it and you'll see the type of phone that comes up. One thing important is that in an IP telephone, its connectivity, its physical connectivity is through um, RJ45 connector, not the RJ11 connector of that is used for a normal analog phone. So if we want to define the IP telephone, it is the end device allowing humans to place and receive calls. And what is a media gateway controller? It provides the overall control of the calls between IP phones, allowing the caller to locate a caller uh, and then forwarding. Now, how do we ensure interconnection with other IP phone if we have an IP phone with us? And first of all, this IP phone has to interoperate with PSTN or other IP phone systems also. Two additional components needed for such an interconnection are the media gateway and the signaling gateway. The media gateway is responsible for converting your uh, voice, which is basically the analog voice, through some codec into a digital format, and which might have different types. For example, the basic type is G.11, and afterwards it would be converted into the IP format, which means that this bit stream, parts or the chunks of this bit stream would be placed in the payload part of our IP packets, and these IP packets would traverse the whole IP network independently, but they would reach the destination uh, in sequence and with maximum possible uh, integrity, so that the communication is flawless and of good quality. The second thing is the signaling gateway. The signaling gateway, as the name shows, it is responsible to initiate the call, um, terminate the call, tear down the call, monitor the call, do billing if required, and all the signaling functions that are done by a signaling gateway. So if we have got a simple analog telephone and an IP telephone, they can communicate with each other, but the parts or the boxes that come in between would be like that. The analog telephone is connected to the PSTN network, and the PSTN network has a connectivity with not only a media gateway controller, it has connectivity with the media gateway as well as a signaling gateway, which are further connected. All three are further connected to the internet, and to the internet we have got the other side of our communication, which is the IP telephone. Basically, media gateway converts our audio between IP network and PSTN network, and signaling gateway translates signaling from PSTN to this voice over IP network. If we see the signaling protocols, we have two major protocols, the H.323 and SIP. H.323 was invented by ITU, as already discussed. It defines four elements that comprise a signaling system, and these four elements are terminal, which is the IP phone; gatekeeper, which provides the location and signaling functions and coordinates the operation of a gateway; then the gateway, which is used to interconnect IP phone with the PSTN. It is responsible for to convert the IP packets into the PSTN format. Both are digital, but on the IP side we have an IP packet, and on the PSTN side we have got a sequence of zeros and ones, which may basically be a DS0 signal or an E0 signal. So that those E0s or DS0 signals are converted into IP packets by putting those putting different a particular size of chunk, a particular chunk of equal size from this uh, binary stream into the payload part of the packet, and putting the remaining one, the next chunk into the next packet, and then the next chunk into the next packet, and so on and so forth. Then the next part is the multi-point control unit, which provides the services like multi-point conferencing. As you know, in the latest systems, we do have voice and video conferencing systems. Now, the other system is the SIP, or the signal or the session initiation protocol, which is developed by IETF, Internet Engineering Task Force. Its main parts, it has got basically three main parts. Number one is the IP phone, as we have in the H.323 also. Then we have got location servers, and then we have got support servers. And the location servers, what do they do is that they store the information about user's location or the IP address. And in the support servers part, what do we have? We have got proxy servers, redirect servers, and registrar servers. In H.323, it consists of a set of protocols that work together to handle all aspects of communication, which include the transmission of digital audio phone call, signaling, to set up and tear down of calls, allowing transmission of video and data while a phone call is in progress, sending a binary message, incorporating protocols for security, using a special hardware multi-protocol unit for conference calls, and it defines the servers for address resolution and counting features also. In this diagram, you can see the different layers that are being used by H.323 while while transmitting a voice over IP. You can see that all the three layers are mentioned here explicitly. On the layer 3 we have IP, and we have got Internet Group Management Protocol, which is primarily used for multicasting. It is normally used for in the case we are going to have conferencing. Then we have got RSVP, which basically ensures that a certain amount of resources are allocated for a particular class of service. So we can define different classes of service, including uh, priority, or then real time, and then best effort. Normally, the internet access, or the you know browsing, which is done on HTTP, it is basically given the status of best effort. Best effort basically means that with the least priority. After that, we have the options of using TCP and or UDP. TCP and UDP both are used for signaling, basically, but for audio, video itself, and for registration, we use only UDP. To send us data while a communication is in progress, we use TCP. Similarly, security options are included in it while we use TCP and UDP both. On the fifth layer, what we have is to send audio and video, we use uh, RTP, real-time protocol, and RTCP. And in addition to that, the signaling, for signaling we have got H dot 225, uh, then H dot 250, then H dot 245, H dot 250. Then for registration, H dot 225, 9 RAS. For audio, we have got a range of options, a range of different codecs that we can use. We can use G.711, we can use H.263, G.722, G.723, G.728, and on the video side we can use H.261, H.323, and to send data we have the option of using T.120, and for security we can have H.3235. I would like you to refer to table number 12.1 given on page 486 of, of the book also, in which you can see how we can have different codecs, and how those codecs are handled in an IP network. For example, uh, the basic format is G.711, which is shown here on top also. In this case, the voice bit rate is 64 kbps, as you all know. So the voice frame size would be 80 and the header bytes would be, and I'm talking in terms of bytes. Number of bytes in the header would be 40, and the packets, how many packets can go in 1 second is 100. 100 packets can go in 1 second. Keeping this these values, uh, we can find out the actual the bit rate when we have converted into the packet IP packet format. It becomes 96 kbps, as compared to 64 kbps, which was available in um, uh, simple data form, simple data, or a stream data form. So this would seem a bit absurd that if it takes more data to send one voice channel, why are we, after uh, converting our normal data stream into IP packet? Actually, there are many other advantages of using an IP packet in comparison to uh, this in comparison to a simple digital stream of bits. So we'll see that in further study also. Let's move forward. What are the characteristics of SIP? Basically, it operates at the application layer, as we have already said. It encompasses all aspects of signaling, for example, location of call party, ringing of phone, accepting a call, etc. Then it provides services such as call forwarding, and it can use IGMP for multicast, for which is used for conference calling. It allows two sides to negotiate capabilities and choose the media and parameters that are possible and acceptable on both the sides. What SIP does is that it creates a URI, Universal Resource Identifier address of each end, and this address looks like an email address. For example, it has uh, uh, an uh, for example, um, a SIP address is sip:bob at somewhere.com. So this is an example of a universal resource identifier in SIP. There are 6 message types which are also known as methods. These are basically uh, signals that go from one place to the other, and which do all the signaling part. For example, there is an invite method or invite message, then we have got acknowledgement method, then we have got buy method, then there's cancel, register options. These are different methods that are used normally. Now, this diagram gives you a very clear method by how a user agent A, which is an IP telephone, it gets connected to a user agent B, which is its destination telephone. How do we get connected? First of all, it requests a query to the DNS server and gives a DNS query about the intended destination. DNS server returns its response, and according to that response, uh, a proxy server is sent an invite. It replies with uh, with its and, with the ringing tone, or not the ringing tone, but the uh, initiation of the call tone, which we call a trying. So it takes some time, and in the meantime, what it does, it sends a query of that particular uh, destination to the location server. Location server gives it the response, and then the proxy server sends that invite that has been initiated by user agent A to the user agent B. User agent B uh, gets the ringing tone back, and this ringing tone is sent to the user A. In the meantime, the user B starts ringing. One more thing, the ringing current does not come from the exchange or the gateway or the media gateway or the media gateway controller, because we do not have a particular central exchange in this case, as we had in the PSTN network. So what happens is that uh, the agent B, it initiates its ringing to tell its user that somebody wants to talk to you, although the CLI facility is available in that. Now what happens next is that that ringing tone, it goes back to user agent A, which initiated the call. uh, it says then, and after that, when it picks up the phone, it sends an OK message, then an acknowledgement message goes back. When the acknowledgement goes back, then the media is issued, or the media uh, link is established. So media session starts, in which the voice goes from one side to other and the other side to the first. After that is after the talking is done, the user agent B can, when it hooks on, when it puts the receiver on hook, basically what it wants to do, it wants to hang up now. So when it does so, a buy uh, message goes back to the proxy server. Proxy server sends that to the user agent A, and it sends back OK and signal, and the OK signal is then further sent back to user agent B. So it is quite clear from this diagram how this voice over IP call is made. Now, how do we have telephone numbers? We do have telephone numbers in voice over IP also, and similar to the PSTN system, uh, different blocks of telephone numbers are allocated by the regulatory authority. For example, PTA in Pakistan, they allocate a certain block, but uh, and that basically block is called the E.164 standard block. But SIP uses its own addresses, which are like sip.smith@uottawa.ca. This is an example, for example, but it maps the two numbers also. For integrated network, two problems are defined. First of all, locating the user. Then secondly, finding an efficient route to the user. So IETF has proposed two protocols. First of all, it is the enum, uh, in which we have got E.164 numbers, and then the TRIP, in which which is basically the telephone routing over IP. What enum does is that it converts a telephone number into a URI, or uniform resource. Actually, I've said universal resource. I don't know if it is uniform resource identifier. And you can see that it converts it so easily. For example, if it is 1-800-555-1234, it converts it 4.3.2.1. We are going reverse, then dot E164, and so on. Now, what TRIP does is that it finds a user in an integrated network. It is used by location server or other network elements to advertise routes. The same process of advertisement of routes is done in TRIP, which is used for voice over IP systems, as done in the data networks. So, but it has its own different protocols. Dividing the world, it divides the world into a set of IP telephony administrative domains, or ITADs. Now, one thing that is very good about our conventional phones is that we do not need to put a power source to our telephone sets. All the power they get the from the exchange only, because the exchange has a complete set of battery system, and that battery is passed on to the user, which is used for its voice transmission and all the signaling, including the ringing. Currently, the IP telephones have to depend on external source of power, but uh, they are trying to develop some systems in which they do not have to um, have a power supply, and they work without a power supply separately. To summarize the whole thing, first of all, IP telephone or voice over IP refers to the transmission of voice telephone calls over IP networks. It is a hot area of research, and also it is used all over the world right now. And basically, I would like to tell you that the basic conversion process that started in the service provider companies was that it came from uh, uh, first of all, they converted uh, the uh, the function of the transit exchange in the form of, and they created C4 exchanges, which were responsible for converting certain numbers of E1s into uh, the data packet format, and those data packets were handed over to the routers of the national IP data networks, and those were handled by the routers to reach the other ends, all other ends. The first one of the biggest challenge for the voice over IP is the backward compatibility with the normal or the conventional PSTN network. The complexity of IP telephony is on signaling. Both ITU and ITF propose signaling standards, for example, H.323 for ITU, and SIP or Session Initiation Protocol by IETF, Internet Engineering Task Force, offering similar functions to each other, but SIP is considered to be a bit simpler. But both are basically competing protocols. H.323 uses a set of protocols for call setup and management. SIP uses a set of servers to handle various aspects. Enum maps and E.164 telephone number into uniform resource identifier using SIP URI, which is quite similar to an email address, as we have discussed earlier. TRIP provides routing among IP telephone administrative domains, which divides the world into different domains, basically, so that it is easier to locate a particular user. Then IP telephones depend on external power, while the uh, normal telephones or PSTN telephones do not. Thank you very much.